In order for a battery or supercapacitor to be efficient, the resistance of its electrodes must be as low as possible. This is an indispensable feature especially in supercapacitors. In EDLC electric double-layer capacitor, the use of carbon, and its various forms, graphite, activated charcoal, graphene, hard carbon, nanotubes, it guarantees chemical inertia to corrosion by the various electrolytes used and relatively low resistance. But since the electrical resistance of carbon is always higher than that of metals, it is necessary to resort to a low-resistance metal collector. Copper and aluminium are excellent candidates, and when compared to the costs, aluminium seems to be the most affordable. Here however, a problem arises, because if we have the two elements carbon and aluminum in contact with each other, and in the presence of an electrolyte we will have corrosion of the element with lower electronegativity, in this case the aluminum collector, and slowly turn first into oxide, and then into aluminum hydrate, in the case of aqueous electrolytes. The consequence will be first an increase in electrical resistance and then the dissolution of the collector. A classic example can be seen on video. The supercapacitor worked fine at first, but then the corrosion process began, of the two collectors of course in the areas where carbon and aluminum are in contact with the electrolyte. The solution to overcome this problem is to completely encapsulate the aluminum collector in a waterproof graphite casing, which guarantees electrical contact but completely isolates from the electrolyte. The free side of the collector is then sealed by a polymer insulator. On the screen, a supercapacitor electrode with a fully encapsulated aluminum collector. This electrode is constructed in layers: insulating polymer layer, aluminum sheet, graphite sheet, activated carbon layer. The materials used to make these electrodes are low cost and easy to find: graphite micrometric powder, carbon black nanometer powder, activated carbon, polyvinyl acetate glue, distilled water, aluminum foil from 8 to 10 microns, and 40 to 50 microns, carbon black conductive glue, sealing glue. Now a video on how to build these electrodes. Starting with attaching the aluminum manifold to the graphite sheet. Material used: 0.6 mm graphite sheet, 50 micron aluminum foil, glue formed by nanometric powder of carbon black and polyvinyl acetate. On the aluminum foil that makes up the electrode collector, I spread a thin layer of conductive glue based on polyvinyl acetate and carbon black, with the help of a plastic foil. I place the aluminum foil on top of the graphite sheet which it is to be glued. At this point, I put a sheet of polyethylene on top of the first steel plate, then the electrode and the other sheet of polyethylene. The function of the two polyethylene sheets is to prevent the glue from sticking to the steel plates. On the polyethylene sheets, it cannot adhere and comes off easily. All that remains now is to put everything under the action of a press. Here I use a self-made press using a hydraulic jack with a capacity of 5 tons. Then on the electrode, which has a surface area of 100 square centimeters, I can develop a pressure of 40 to 50 kilograms per square centimeter. Since the electrode had to remain under pressure for 24 hours, I had to use the 4 clamps. After 24 hours, I proceed to open the 4 clamps. And to remove the 2 plates containing the electrode. Thanks to the non-stick properties of the 2 polyethylene sheets, it is easy to remove the electrode without damaging it. Without these sheets, the burrs of the conductive glue would have welded to the 2 steel plates. The graphite sheet is now perfectly welded to the aluminium manifold. All that remains is to cut the bows of the conductive glue with scissors. Now all that remains is to spread a layer of insulating polymer on the side of the aluminum foil. The technique used has been extensively described in my previous video, Flexible Graphite Sheets for Batteries. The same technique was used to make the graphite sheet. Now the electrode should be left to dry for 24 hours. After 24 hours, the protective coating formed by polyvinyl acetate and aerosol adhered perfectly to the aluminum and graphite foils, ensuring the protection of the aluminum manifold. Now all that remains is to coat the electrode with a layer of activated carbon, which is essential for use in supercapacitors. To this end, I use as a starting material the activated carbon used in aquarium filters. Activated charcoal must first be ground to reduce particle size, and then passed over a sieve to select particles equal to or less than 680 microns. As you can see from the photo of the sieve. To grind activated charcoal, I use a mortar with its pestle. Everything must be ground until you get particles on average between 50 and 600 microns. and with the sieve, I removed those above 680 microns, which must be regrind. On the screen you can see the formula for the preparation of the activated carbon coating, to be applied on the electrode. In a glass cup, I weigh 4 grams of activated carbon and 3.5 grams of polyvinyl acetate. I stir the mixture thoroughly. And add 3.5 milliliters of water solution and isopropyl alcohol. Now the mixture is ready for printing. Now, I apply a layer of this activated carbon mixture on the electrode, with the usual technique, already described in the video, flexible graphite sheets for batteries. For printing, I use a 1 mm thick plastic frame, that allows me to obtain a layer of activated carbon of 0.6 mm perfectly welded to the graphite plate. In the end, the electrode takes 24 hours to dry completely. After 24 hours, from molding, the electrodes are ready for resistance measurement. Now two measurements on the resistance of the electrode to the passage of current, the first on an electrode with a 50 micron aluminum collector. Resistance is 0.5 to 0.6 ohms. This is the measurement on an electrode with a 10 microns aluminum collector. Resistance is 0.6 ohms. Conclusions. Thank you for your attention. To the next.